In this lesson, we are going to learn about nuclear stability and binding energy per nucleon. What decides the stability of a nucleus? Stability of a nucleus is decided by binding energy per nucleon, not the total binding energy. It is binding energy per nucleon. If you make a graph of binding energy per nucleon against mass number, we get a graph like this. The first nuclide that has got more than one nucleon is deuterium, isotope of hydrogen. This is somewhere here. Helium nucleus is much more stable than any of its neighboring nuclides in the periodic table. The binding energy per nucleon for helium nuclei is much more than its neighbors in the periodic table. Because this helium nucleus is very stable, that's why alpha particles are produced in radioactivity. You might have been wondering why alpha particles are produced. Why not lithium? Why not protons coming out? Why not neutrons coming out? Why does alpha particle come out, which is nothing but helium nucleus? The reason is helium nucleus is very stable. It has got a high binding energy per nucleon compared to its neighbors in the periodic table. Now, as we increase in mass number, the nuclei become more and more stable. Up to iron 56 and nickel 62. These are amongst the most stable nuclides. The binding energy per nucleon for iron 56 is 8.75 MeV per nucleon. The binding energy per nucleon for nickel 62 is 8.794 MeV per nucleon. Now, as we increase in mass number, the binding energy gradually falls and it becomes around 7.6 MeV per nucleon for uranium 238. So, a nucleus which has got more binding energy per nucleon will be more stable. A nucleus which has got less binding energy per nucleon will be less stable. Now, so that is an important point we have learned. Binding energy per nucleon decides the stability of a nucleus. The greater the binding energy per nucleon, the more stable is the nucleus. Therefore, in a nuclear reaction, energy will be released when total binding energy increases. Let's look at this reaction, a nuclear reaction. X is becoming Y plus Z. The mass number of, say, X is, say, 100. Y is 60. And Z is 40. These are the number of nucleons, right? X has got 100 nucleons, Y has got 60 nucleons, and Z has got 40 nucleons. The binding energy per nucleon of X is, say, 7, Y 7.5, and Z 8. Now, here binding energy is obviously increasing. So, energy will be released in this particular nuclear reaction. Question is, what is the energy released? This binding energy per nucleon is in MeV per nucleon. So, how to find out the energy released in this nuclear reaction? Energy released will be binding energy of products, total binding energy of products, remember that, minus binding energy of reactants. So product is this one first, having 60 nucleons, and the binding energy per nucleon is 7.5. So 60 into 7.5. Same way here, binding energy per nucleon is 8 and the number of nucleons is 40. So 40 into 8 minus binding energy of the reactant, which is there are 100 nucleons and each of them, or the binding energy per nucleon is 7. Right? So what do we get? We get 70 MeV. Therefore, in this nuclear reaction, 70 MeV of energy will be released per reaction. Right? So how do we calculate that? Energy released is binding energy of products minus binding energy of reactants, total binding energy. Therefore, in a nuclear reaction, energy is released when total binding energy increases. Let's look at this graph now. If you go from here to here, binding energy is increasing, right? And this process is nuclear fission. Nuclear fission means a heavy nucleus breaks into two parts of almost equal mass numbers. Right? This heavy nucleus can break into two parts and energy is released. That's what we call nuclear fission. This is the source of energy in atom bomb, nuclear reactors. Here also binding energy increases as we go from light nuclei to heavy nuclei. When two or more light nuclei combine to form a heavy nucleus, then also binding energy increases. And this process is called nuclear fusion. Nuclear fusion is the source of energy in hydrogen bomb and sun, stars. The entire energy coming from all these heavenly bodies, sun, stars, etc., is due to nuclear fusion. So in this lesson, we have learned that binding energy per nucleon decides the stability of a nucleus. Greater the binding energy per nucleon, the more stable is the nucleus. The most stable nucleides are iron 56 and nickel 62. Binding energy increases when a heavy nucleus breaks into two or more parts having almost same mass numbers. That is called nuclear fission. And that takes place in an atom bomb and a nuclear reactor. Binding energy also increases when two or more light nuclei combine to form a heavy nucleus. This is called nuclear fusion. This is the source of energy in a hydrogen bomb, in sun, in stars. In fact, we have not been able to build a controlled nuclear fusion reactor. If one of you build a controlled nuclear fusion reactor, definitely get a Nobel Prize. And because this will be a very good source of clean energy. You can get almost an infinite amount of energy from this nuclear fusion reaction. And the products of this nuclear fusion reaction are not dangerous. Products of nuclear fission are dangerous. That's why people have some apprehensions about nuclear reactors. Now in this lesson, we are going to talk about magic numbers. Sounds interesting, right? We have seen the graph of binding energy per nucleon against mass number. This is the graph we get, with deuterium being here and here lead 208, uranium 238, here you got iron 56, nickel 62. Now some nuclides like He42 have more binding energy per nucleon than their neighbors in the periodic table. In fact, it is observed that nuclides having 2, 8, 20, 28, 50, 82 and 126 nucleons of same kind are more stable than nuclei of neighboring mass numbers. Nucleons of same kind means either protons or neutrons. So if a nucleus has got these many numbers of protons or neutrons, nucleons of same kind, then they are more stable than nuclei having neighboring mass numbers, nuclei of neighboring mass numbers. These numbers are called magic numbers. So magic numbers are 2, 8, 20, 28, 50, 82 and 126. Remember that.